So this lecture is going to talk about the ideal gas law. And if you recall, so far we've discussed three gas laws. We've looked at Boyle's law. We've looked at Charles' law. And we've looked at Avogadro's law. And when we think about these laws, you might recall that Boyle's law had told us that pressure and volume are inversely proportional. And we can say that mathematically by saying PV equals some constant K. And what we mean by that is if we were to increase the pressure, then the volume has to decrease so we can still be equal to the same constant K. By contrast, when we looked at Charles' law, we said we said that volume and temperature are directly related. And so when we think about a gas, what that's saying is when we have Charles' law, mathematically volume over temperature is equal to some constant. Or put it that another way, if we increase the volume, then the temperature also has to increase so it stays equal to the same constant. And in a very similar fashion with Avogadro's law, what this is saying that the volume and amount of a gas or moles of a gas are directly related. So that tells us that we can write a similar equation. So the volume over the number of moles N is equal to some constant. And similar to Charles' law, if the number of moles of a gas decreases, then the volume of that gas also has to decrease so we can maintain the same constant K. Now, with all of these laws, Boyle's law, Charles' law, and Avogadro's law, we're always looking at two variables, and all other variables are held constant. So when we look at Boyle's law, for instance, if we're looking at Boyle's law, we're changing pressure and volume, so the temperature and the amount of the gas has to remain constant. And with the ideal gas law, what we've done is we've taken all of these laws together and come up to a single equation that can express all of these. So our ideal gas law is pressure times volume is equal to the number of moles times some constant R times the temperature. And R in this equation is the universal gas constant. And here, the power of this is that we now have a single equation that represents all of the variables of our gas. And when we think about what an ideal gas is, we can define an ideal gas to be any gas whose behavior is predicted by the linear relations of the ideal gas law. And so what that means is anytime we have an ideal gas, it just means it obeys this mathematical equation. And when we think about what that means physically, an ideal gas is a gas in which the gas molecules don't interact with each other. So they are all separated from each other. Now, What's important with the ideal gas law is we now have a predictor where we can change more than one variable. So for instance, we know if we know the pressure and the volume of a gas, and if we add some amount of moles, we can say what's going to happen to the temperature. Or maybe we have a balloon, and at the surface, at atmospheric pressure, we know the volume and we know the temperature, we know the moles. We can let that balloon go up into the atmosphere. And when it goes up into the atmosphere, you can think about what's going to happen. Well, when you go up in the atmosphere, the temperature is going to decrease. We know the pressure is going to decrease. So we have to think about, well, what's going to happen to the volume? And now we're going to be able to quantify that using the ideal gas law. This universal gas constant, if we think about what R is, we can think about our value of R, and we can find R by rearranging our ideal gas law equation and say R is going to be equal to PV over NT. And so if we're at standard temperature and pressure, so at STP, we know that R is going to be equal to 1 atmosphere times R 22.414 liters. So that is the volume of 1 mole of gas, 1 mole, and divided by 273.15 Kelvin. So if we multiply and divide that out, we find that the value of the universal gas constant is 0.08206 liters times atmosphere divided by moles times Kelvin. So here is the value of our universal gas constant, which is going to be, it is a constant, it is always going to be the same for these given conditions. But the other thing you should take note of is we can find other values of R where the units have changed. So we can also have a value of R you may have seen before, that's 8.314. That's the same R, but the units are these, oops, made a mistake, let me fix that, kilopascals times liters over moles times Kelvin. Or we can have 8.314, and the units of this would be joules over mole times Kelvin. So it's always the same value of R, but we do have to watch out for the units given in the problem to figure out what value of R we need to use based on that. So we can go through one quick example. So here's a quick problem of using the ideal gas law. And we can say how many moles of gas, and in particular air, are in the lungs of an adult with a lung capacity of 3.8 liters. And we're going to assume that this person is standing in a position where the pressure is 1.00 atmospheres and has a body temp of 37 degrees Celsius. Okay, so here's our problem. So again, whenever we have a problem like this, I like to dissect it and say, what are we looking for? We're looking for moles, so how many moles? All right, so we are given, we can dissect the problem and say, what are we given? We're given a pressure, we're given a volume, and we're given a temperature. And so we're going to use the ideal gas law, PV equals nRT. We're looking for moles, so we want to say N is equal to PV over RT. And then we can say, well, what do we know? we know the pressure is given as 1.00 atm. We know the volume is given at 3.8 liters. We know R is the universal gas constant, 0.08206 liters times atmospheres mole times Kelvin. And finally, we know the temperature is equal to 37 degrees Celsius. But the thing to watch out for is we need this to be in Kelvin. And so I'm going to rewrite this temperature Kelvin is equal to 37 degrees Celsius plus 273, which equals 310 Kelvin. So now we can come back to our equation and say number of moles is going to be equal to 1.00 atmospheres times our volume, 3.8 liters, divided by our universal gas constant. I like to write out the units so I can cross them out to make sure we're going to get the right answer. And then times our temperature of 310 Kelvin. We can now cross out units. Atmospheres, cross out with atmospheres. Liters, cross out with liters. Kelvin, cross out with Kelvin. And we're left with moles on the bottom of our fraction of a fraction. So that's going to flip up to the top. So the number of moles is going to be equal to 0.15 moles of gas in the average adult lung. Thank you.